So what I'd like to talk to you about now is Poisson time series. So what do I mean by that? Well, let's start with talking about what we mean by a time series. A time series generally means we have repeated measurements of the same thing on a fixed schedule. So today, the government released its revised estimates for GDP growth in the last calendar quarter of 2014, last year. So there is a schedule in which GDP growth estimates are released, a regular schedule. Or it could be something that happens monthly. Every month there's an estimate of the unemployment rate. Every month we, can measure things about health, right? Or week or day, right? How many people died last month, last week, yesterday, right? That's something that occurs on a regular schedule. And that is a time series. Now, if we do that for two variables, we can ask the question, are these time series associated with each other? Does A tend to go up and down with B? And so that's what a time series analysis is. It's looking at the association between two different variables, each of which is a time series. If the outcome variable is a count, like deaths, then that is a Poisson time series. Why? Because it's a time series of Poisson events, events that follow the Poisson distribution, counts. So I'm responsible for this. Time series analysis has been around for a long time, but Poisson time series analysis I introduced. And I introduced it to look at the association between daily deaths and daily air pollution. Because the question was, does air pollution kill people? And there was evidence that that was true from a number of disasters that occurred in the Western world due to rampant production of pollution without controls. So in 1931, the Meuse Valley in Belgium is a valley. It's not very deep, but it had lined with chemical plants. And those chemical plants put out huge amounts of pollution. There were no controls. They got a very low-level inversion layer that trapped all that pollution in the valley. Concentrations skyrocketed. No one knows how high because they weren't really measuring it. And there was a small town in that valley that had as many deaths in the next week as they normally had in 6 months. In 1948, in Donora, Pennsylvania, there was a similar problem where an industrial facility put out a huge amount of smoke. Again, an inversion layer trapped it. And, they had people on gurneys in the hospital corridors because they didn't have any place to put them. And then in 1952, there was again an air pollution disaster in London, and 4,000 extra deaths occurred that week. And then the rate stayed elevated for another couple of weeks, and it looks like there were about 10,000 deaths attributable to that episode. So we know that short-term excursions in air pollution can cause deaths. But these were all very high levels. And the question is, what about lower levels of air pollution? And to look at that, you know, it's not going to be, it's a smaller signal. You're not going to see a dramatic response. We need to do some more continuous analysis, like looking at the association of these two time series. And the nice thing about this kind of study is, you know, one of the first ones I did was in Philadelphia, and in 10 years there were over 200,000 deaths in Philadelphia. It's a big city, right? And so you have a lot of power to look at association because there are a lot of events. Now, you've seen this before. You've actually done a Poisson time series. You were looking at daily deaths in Chicago and daily temperature in Chicago, right? And so without really discussing it as a time series, we've already done it. And also, this has some connection to the discussions we've been having talking about heart rate variability and within subject versus between subject variation. Because in the time series, we're looking at a within city variation in deaths and variation in temperature. And so confounders that vary between Chicago and Cincinnati aren't going to matter. There are some confounders, and we'll go into this in more detail, that are going to turn out to be eliminated by design. Now, on the other hand, what are the major predictors of death? I mean, smoking, right? Did you control for smoking when you looked at temperature and mortality in Chicago? No. Diet? Serum cholesterol, and by the way, those new guidelines don't say anything about serum cholesterol not being a risk factor for cardiovascular disease. They say that since your body makes cholesterol, the amount of cholesterol in your diet isn't a good predictor of the amount of cholesterol in your artery. So there are all these predictors, and we obviously don't have any measurements of them in these time series studies. And since we don't have a measurement, we didn't control for them. Well, that sounds a little disturbing. And when I first started doing this, some people went nuts. They said, you didn't control for anything. So let's think about that problem. Suppose I did the alternative. I controlled for everything. Here's my study design. I'm submitting the R01 next week, okay? I'm going to recruit the entire population of the Boston metropolitan area, 2,500,000 people. And I'm going to have a remote monitor on them connected to their cell phone that sends into my computer here at Harvard daily measurements of what their individual exposure is, and daily measurements of their blood pressure, daily measurements of their smoking, daily measurements of their diet, etc. So I now have 10 years of data. That's 3,654 observations times 2.5 million people. Eat your heart out. Nurses' Health Study. Have I got a big N? And for each of those people, either they died yesterday or they didn't. So I'm going to do a logistic regression. Yes, no, person died, controlling for all their risk factors and looking at particle concentrations in the air. May cost a little bit, but hey, for science, we have to make sacrifices. So the question I'm going to ask you is, what's the difference between that study and the one that I actually published? And the answer is, if it turns out that the rate at which people smoke cigarettes doesn't fluctuate from day to day with the particle concentrations outside, and why would it? Then it doesn't matter whether you control for smoking or not. And if the amount of drinks you have each day doesn't go up and down with the amount of air pollution in Boston. And how many of you know how much air pollution there is in Boston today? None of you, right? And you don't know what it was yesterday. You don't know it. You can't perceive it. It's not going to drive how much you drink, okay? And since the probability of each of you dying today is small, then that logistic regression turns into a Poisson regression, because in the limit of low probabilities, the binomial distribution converges to the Poisson. And since none of these variables are confounders, I'm clearly going to get the same coefficient either way. I just saved a lot of money. So the goal of time series analysis is to make sure that what I just said is really true, that I don't have any correlation between the confounders and air pollution. And some of that will happen automatically. Some of the predictors of mortality, age, race, sex, they don't actually fluctuate much over time. So by only looking at temporal variation in exposure and temporal variation in mortality rates, tant pis. Some of these things may change, not in correlation of day-to-day variation in air pollution, but they may have a long-term pattern. Think about smoking, for example. You want to smoke at work, you have to go outside. Possibly people do that less often in the winter because it's really cold and uncomfortable outside. So maybe there's some seasonal variation in smoking. I don't know that that's true, but it's possible. So if there's also seasonal variation in air pollution, then smoking and air pollution might be correlated. So we want to do something about that. Or there's been a long-term downward trend in air pollution in the US. Well, there's been a long-term upward trend in statin use. So just because they have long-term trends, there's some correlation between those two variables. So that's a potential confounder. On the other hand, day-to-day fluctuations in statin use or in cigarettes per day are unlikely to be correlated with air pollution. So what I mean by filtering is to take the longer-term patterns over time and remove them so that the confounding is gone, because we don't think there's any short-term correlation between fluctuations in time in air pollution and fluctuations in time in the confounder. So the correlation exists, but on different time scales. And in particular, there's plausible correlation on longer time scales, fluctuations over many days, but not on shorter time scales. And so we can think about resolving the time series into long-term trends, slowly changing seasonal patterns, and the rest. And the idea is that the confounding potential with smoking or other alcohol use or statin use really only exists on these longer time scales, and it's just implausible here. And so if we can throw these away, then confounding has gone away. So, you know, if I'm looking at the short-term fluctuations from day to day, then smoking history, I'm matching on smoking history. The smoking history of the population today and yesterday was the same. Same with socioeconomic status. It doesn't change day to day. Age, etc. Those things either have no fluctuations over time or very long time scale fluctuations. And so that's what I want to do. And I said I'm going to do that by filtering. So again, I've mentioned this and this and this. So let me go on to talk about filtering. So in a repeated measures study, we know that body mass index differs from person to person, and possibly the exposure that we're interested in differs from person to person. But if I put in a dummy variable for each person, then variables like body mass index are controlled for by design of the study, and even variables that vary from person to person that I didn't measure have been removed by controlling for subject. And that's the same idea that we have in time series, that if the potential confounders are only correlated with sort of longer wavelengths or time trends, changes in exposure, then if I remove those patterns, then I've controlled for those confounders, measured or unmeasured. Okay? And so I do that by fitting splines for time. That's how I'm going to remove those patterns. And how do I remove a long-term pattern? Well, I could fit a spline with a few degrees of freedom because it may not be linear, and that would clearly take out a long-term pattern from my time series. But what if I have 10 years of data and I want to control for season? Well, then I might think I need 4 degrees of freedom for each season, and I put in a spline that takes out not merely the long-term time trends, but also the shorter-term seasonal variation. And so I think it seems natural to think that by varying the degrees of freedom that I use for time, I can take out longer-term time trends in the pattern of air pollution and in the pattern of mortality. And the more degrees of freedom I use, the narrower and narrower window of the time trends that are left. But remember, time is not a real variable here. Time doesn't predict mortality. Nobody dies because it's October 22nd. People die on October 22nd. They die because they're smokers, or they die because they didn't look both ways before crossing the street. But they didn't die because it's October 22nd, right? Time is a surrogate. It's standing in for variables that we didn't measure. These long-term trends and seasonal variations in unmeasured variables, which might, on those same time scales, be correlated with our exposure of interest, be it air pollution or temperature, but which we don't think are correlated on very short time scales. And so the decision of how many degrees of freedom to use in this spline is a decision of how short the time scales we want to focus on should be in the relationship between temperature and air pollution and mortality. Well, cross-validation or Akayeki's information criteria or any other way that you might use in a penalized spline to choose lambda isn't really asking that question. The question isn't how many degrees of freedom does it take to fit the relationship between time and daily deaths so that you fit all of the temporal pattern and no noise. The question is, how many degrees of freedom do you need before you now think that the remaining fluctuations are short-term enough that there's no correlation with smoking or alcohol use? Cross-validation has no way of telling you that, right? So you need to decide. And so simulation studies have looked at pretty complicated temporal patterns, like you look at the temporal pattern of pneumonia, for example, simulate data like that, and ask, how many degrees of freedom do I need to just get down to short-term fluctuations? And the answer is about 4 to maybe 5 degrees of freedom a year. And so that's what I generally use, 4 to 5 degrees of freedom per year in the spline for time. So if that works, what are the remaining potential confounders? Well, if I'm focusing on temperature, the other potential confounders are other weather variables. I mean, if temperature fluctuates day to day, so does barometric pressure. Maybe that's a confounder, right? Air pollution fluctuates day to day. Maybe it confounds temperature. If I'm focusing on pollution, weather is a potential confounder, right? But the potential confounders are things that fluctuate day to day and are probably correlated. So if barometric pressure was uncorrelated with temperature, don't worry about it, right? If you're looking at temperature. But if it is correlated with temperature, you have a problem. If temperature and air pollution are correlated, then they're potential confounders of each other. So these are the things that we need to worry about. So how do I do that? Well, so I might fit a model of the log of the expected value of y, right? Count data, daily deaths are counts. There's an intercept, there's a coefficient for particles, and then I think temperature and humidity might be confounders. And I put in penalized splines here, right? This is a penalized spline, and it has nothing in it. It just says do a penalized spline. So if you just say S of temperature, then the GAM function knows that you want it to use cross-validation to decide how many degrees of freedom. And that seems valid because We know it's not likely to be linear, but we don't really know what it looks like. Let's let the data decide, okay? So in that case, I do use a penalized spline. I put in dummy variables for the day of the week because more people prefer to die on Monday. And you got to honor their preferences. And then I control for date. So this is 10 years. I'm going to use 40 degrees of freedom. But I told you I don't want the computer to decide how many degrees of freedom to use. I'm not using a penalized spline. So the way I tell it that not to use a penalized spline, to use just a plain vanilla spline, is fixed equals true. And then I tell it how many knots to use. So this is going to fit a spline with 40 knots, and it's not going to penalize anything because that's how many knots, how many degrees of freedom I want to use to control for season and long-term time trends. And then I'm going to say quasi-Poisson because the data might be over-dispersed. The variance might be larger than the mean. We talked about that. And I tell it what data to be. So temperature and humidity are real variables. I don't know the shape, excuse me, of the dose response, so I let the penalized spline choose. Now, one other thing that's important about time series. The big problem that we have in observational epidemiology is that exposure is not randomly assigned. And therefore, the people who choose, for example, to take hormone replacement therapy may be different and important other characteristics from the people who choose not to. They assign themselves to the exposure. And therefore, the exposure assignment could be correlated with confounders. And that's why sometimes when you do a randomized trial, you don't get the same answer. Because even though we obviously try to control for confounding in our cohort studies, we can miss things. But the air pollution you got exposed to today was randomly assigned. You didn't choose it. It's not related to your behavior. Mostly it blew in from out of town, right? Because air moves, right? You don't know whether today is higher or lower than yesterday, so you can't modify your exposure to other things in accordance with it. And therefore, this, other than possible seasonal patterns and long-term trends, this is a quasi-experimental design. And that's really a very attractive feature of it, that once I throw out those long-term trends, and other than weather being correlated with air pollution, so those things each confound each other, there are no other confounders. The exposures are randomly assigned. So let's end by walking through an actual example. So this is from a study I did long ago, as you can tell by looking at the dates, and this is daily deaths in Boston between 79 and 86. So I can fit a spline for date. And what I get is something that looks like this. Notice that the peaks are not the same in each winter, and that seems true in the data. Obviously, that peak and that peak are higher than this peak or that peak. So the peaks in the winter do vary from year to year, and we've captured that. And then if we put in the effects of the smooth function of temperature and humidity and day of the week dummies, that fuzzes the curve up. So this is the predicted model without air pollution. And if we look at the residuals of that, they look pretty much like noise. And so if I now add air pollution in, there's no seasonal pattern, no long-term temporal trends in these residuals. It's hard to imagine what the confounders are. So that concludes my discussion of time series analysis. Thank you.